Thank you for having me here. So yes, I am a psychologist and I focus on behavior change, so please be mindful of that when you hear my talk and what I think through with this. But measurement is critical, and I actually want to just piggyback on what David set up. Oftentimes people, I mostly focus on physical activity, and the main reason why is not because I don't care about diet, but it's always because I've never felt comfortable with the measurements I could use. And so I never felt like I could even start to intervene until I had a good solid measure. So just to extend that point. So yes, my task was talking about the state of the technology and innovation related to physical activity and healthful eating. So I'm going to first start with disclaimers. I've been funded by these groups, and I'm an advisor to this startup company. Okay. And here are the takeaways. I'll come back to these at the end, but I always like starting with what I'm going to tell you. So we are moving from a data poor to a data-rich science. And part of what we need to think about is actually developing what I've been affectionately calling usable evidence base, and I'll get to what that means. But doing this requires a pretty major shift in how we think about our measurement, obviously the main focus here, but then also our theories, which, as David teed up very well, is intimately linked with our measurements, and then methods for causal inference. And so I'm just going to run through this through it. So I'm going to first hit in on the problem, right? And I'm going to go through this very fast because you all know these things, right? Health is complex, right? It's multi-level. So, and we know healthcare costs are rising. We know that chronic diseases is a major problem. Obviously, physical activity and diet have a big impact. Obesity is really important, right? We know that behavior explains a large portion of the variance in these outcomes, right? We also know that there's all these multiple determinants, right? And we know that this is dynamic, that these things are changing and interacting with each other, often with behavior at the centerpiece of this, right? What does this set up? A highly complex system. And the question then asks, like, how are you going to possibly understand this with the t-test? That's an extreme statement, right? But that it's an important question to get at, right? This is a complex problem. We probably need complex methods to be able to handle it. And so the interesting thing that has emerged from this then is all the information and communication technologies that are now available to us, right? So toward a data-rich science. So a question that Bill Riley posed, and actually this is a paper that Kevin and I and Bill, lead author, or Bill Riley is the senior author on this. One of the things we got into is this question of, well, what enabled meteorology? I mean, stop and think about this for a second. It's amazing that we know what the weather is like tomorrow. Isn't that? I mean, do you know that chaos theory, the things that things are really crazy and uncontrollable, do you know where that came from? Weather prediction. It's really, really hard to do this, right? But somehow you open up your phone and you get a weather prediction for tomorrow, right? And David pointed out after 10 days, it's crap. That's totally true. But the fact that we can get 1 day, 2 days, 3 days, 5 days, right? And it gets progressively less, but the fact that that exists is actually an amazing scientific feat. So then the question that begs to be asked is, well, what got meteorology to be able to be so amazing that it's now this thing that we literally take for granted in our pockets? If you read into the history on this, if you go to the NOAA website, which I had fun doing, one of the things that you've noticed first is that data started to get interconnected, right? So there were all these separate groups, right? Particularly pre this, it would be like Farmer's Almanac, right? So you had all these farmers who were basically documenting stuff that was going on in their local farms, and they're trying to think through things, right? But then they started sharing information, like, hey, did you notice this? Oh yeah, that's interesting. I noticed this pattern, right? So there started to be this mechanism of sharing, right? But then, you know what they noticed? And this is where the measurement comes into play. They noticed that they were calling things the same thing, but they actually meant something different. It's actually called the jingle-jangle fallacy, if you wanted to dig into the dorky term for it. But basically, people were saying the same, using the same term, but meaning something very different. And so it required data standardization. When you mean Fahrenheit, how are you measuring that? And all of the precision that David was just getting into, right? So that was a critical next step for it that was realized once people started actually carefully sharing and trying to build on each other's knowledge and work. Right? From this, they then started getting into multi-level modeling of this, right? Well, so first it started with just these, land-based measurement, but then, well, what happened? We started getting satellite dishes, we started getting weather balloons, we have a much wider range of ability to actually measure a much wider range of what's going on in terms of weather prediction. Then when they started gathering all this, like, crap, well, we need some kind of computer to manage this. This is really complex. This is where chaos theory started coming into play. They're like, wow, if we have our starting condition here versus there, wow, this thing goes completely different, right? But computational capacity had to grow to be able to handle the level of data complexity that was going on. And then finally, and this is, I think, one of the things that I find particularly interesting, there's this constant iterative improvement now on weather models. And so there isn't one weather model that exists. There's anywhere between 5 and 10 competing weather models that are going on at any given moment. And then a meteorologist now, you know what they do? Oftentimes they're there to have this kind of human-computer interaction with the model, to basically say, I think this model is the one that's going to explain this phenomena for tomorrow in New York City. But I think it's that model that's going to explain this model in Bangladesh, or wherever the heck it is, right? And the really nice thing about weather prediction, and back to this idea of computational models, is it makes a concrete prediction. And so from a scientific standpoint, you make a prediction, and then the next day you find out you're wrong. Well, good. You just learned something, right? How can you constantly work on that, right? So this is actually, I think, a very important analogy that we need to be thinking about for understanding energy balance, for understanding behavior and behavior change writ large. So I'm going to try to set this up and say, I think a lot of this is actually happening right now, and we need to be much more mindful of it. So in terms of interconnected, right, I think a lot of you know about ResearchKit and health kits, and there's a lot of, and obviously the precision medicine initiative that Kevin already mentioned, right? There's increased focus on trying to build a sort of common data infrastructure for this, and I think Sage Bionex has been a major pusher for this. And then in terms of data standardization, this is an example of OpenM Health. It's a group where they've basically been focused on trying to make sure everybody's talking about the same thing. When you measure steps, what does your steps from Jawbone mean compared to the steps from the Withings that I'm wearing right now, or the Fitbits and whatnot, right? How do we actually figure out a way to get that? And as David pointed out, right, in many ways, you can do the corrections about that first type of problem of measurement, but it's really hard when you don't know what's wrong with the measurement, right? And so a lot of their work is actually focusing on that first level of measurement, just like the kind of correctable mistakes of measurement error. But then after this, computational power, right? So you might not know about this, but there's this thing called TensorFlow from Google. It's an open source software library for machine intelligence. So you maybe not know what it is, but you've probably used it or heard about it. It's what built Google Translate, right? And so has anyone ever done this? I was in Germany with Donna, actually, and I couldn't read the German dictionary, so I pulled out my phone and I just looked at it, and it gave me English translation of the thing. So you can see it here, right? There's the sortie in French, right? And then exit, it translates. That's incredible. Right? I mean, that's just totally mind-boggling. This is the technology that built that. And the important thing to note is this is open source. This is available for anyone to use. They want to allow everyone to have the access to this machine power, right? And now getting this back to kind of human and behavior change, right? Now the other example of this is now their new Google Home that's come out, right? I mean, think about this as a computational power, right? Okay, Google, tell me about my day. Good morning, Michelle. The time is 7:21 a.m. The weather is San Francisco, currently 72 degrees. You may want some sunscreen. There's a health message, right? Today at 9:30 a.m. you have a 5K run at Chrissy Field. Have a nice day, right? Think about the level of information that's going on that's combining to find this kind of just-in-time moment, which I know Donna will riff off of later, and I'll get to that in a bit, right? But there's some computational power happening, right? But then the other part of this is this sharing, right? So if you haven't seen this is really great work that Brian Nozak is doing out of University of Virginia on the open science framework. He's basically trying to, there's a technology tool called GitHub, which basically allows you to share code easily. He's basically taking the logic of GitHub and turning it into scientific experiments. So that instead of us constantly reinventing the wheel on everybody writing their own consents and writing their own, every protocol that you have, writing your own interventions, it's all shared publicly and a place where we can build on each other's work. This is exciting and important work. So in some sense, the technology, I think, is very much moving us in the direction of meteorology. We just have to recognize it and take advantage of that. But now we're talking about humans. Right? So we're not weather. We are humans. People have decisions and whatnot, right? So this is where the idea of usable evidence comes into play. And this is a riff off of precision medicine, but I want to try to link it to the human more so. And I was talking with Margaret Laws just yesterday, and she literally told me this quote yesterday, and I was telling her about usable evidence, so I threw it in here. From evidence-based decision-making to decision-based evidence-making, right? And so what do I mean by that? Well, here's the question. What do I do now? Pretty much anybody's asking this question, whether that's a patient or an individual, right? They were trying to lose weight, right? But they're out at a place with somebody else. Oh, this is such tasty food and stuff. I want to totally take advantage of this, right? Or the doctor, I'm trying to help my patient. What do I do now? How do I help them, right? Or even policymakers. I want to figure out how to make my cities healthier, right? What do I do now to try to help promote health in my city? How do I put in more complete streets? What should I do? Will something that worked in New York City work in Phoenix? Will it? I don't know. Oftentimes there are these very concrete questions. Unfortunately, the evidence base isn't necessarily living up to this, And so I think about it as basically a supply and demand problem. There is implicit to that question, there is a certain type of evidence that's being asked for. The type of evidence that takes into account individual differences, that takes into account subgroups, and that feasibly even provides a mechanism to help people learn when the evidence doesn't yet exist. But that's not really necessarily what we're always creating, right? And you can see this even in kind of the experimental design. So let me just show this a little bit visually, right? Randomized controlled trials, particularly things more like the double-blind randomized controlled trials. I'm not talking about randomization. You'll see in a moment. I'm actually a big fan of randomization as well for causation. But randomization, when you're randomizing a person, right, or even cluster randomization, right, you're in essence striving for these. It's almost like we're striving for universal truths in the realm of like Newtonian laws of physics, right? And of course, these are great. When you can figure out how the world works at a level of Newtonian laws of physics, you better damn well do that, right? Because that helps you understand the world. It's the theory for helping you understand a phenomenon, right? But the problem is when you're going back to that setup of health is a complex, multifaceted problem, which means that probably facets of the person, facets of the context where they live, all have an impact potentially on what will work, what actually influences what they're eating, how physically active they're being, and therefore by extension have an impact on their health outcomes such as obesity, right? And so conceptually and also just getting back to the question, right? Again, I think as an interventionist, right? So for me, I want to try to give someone evidence base to help them make a decision. And I want to really put their decision first, right? So based on the question they're asking, this is probably, this isn't right exactly, right? But just imagine this is a rough proportion of how our evidence actually should be doing. And this is setting up a different question on the type of experimental designs we could feasibly be doing, right? And you'll notice one thing that I have here that might seem really strange is idiosyncrasy. It's like, wait a minute, that's not science. That's by definition not generalizable. Correct. But what could be generalizable is the mechanism on how people learn about themselves. Right? And because now you have a tool so that they learn. And so there's examples from computer science called reinforcement learning. It's actually a very simple system. It was actually based on old operant conditioning for those behaviorists out there. In essence, what it does is it sets a 50% probability or some probability estimate, and then it tries something, and then it watches and sees if the outcome that it wanted happened. So it's like you send a text message to go for a walk, and then the next day, in the 30 minutes afterwards, if the person did go for a walk, the probability that they're going to send that notification goes up a little bit, right? And then it goes up and it goes up as it does well or it doesn't do well, right? This is an example of actually a process that is handling idiosyncrasy. And so for me, this is an interesting question. How do we actually start thinking more broadly about this? And so this ultimately sets up this question of, well, how do we create a usable evidence-based for this? Particularly with the decision of the participants in mind. So. And I'm going to hit on 3 core points: digital technologies, theory, and then our research methods, right? So digital technologies, we're going to be talking a lot about this. I didn't get into the great detail and all the great measurement that I'm sure you guys are going to talk about. I saw the program beforehand, so I'm just going to hit this more at a high level, like the types where data could feasibly come from. That was more the way I wanted to go through this a little bit. But ultimately, it's getting very much in line with what David was getting at, right? And for me, as someone who cares a lot about the temporal dynamics of this, and trying to get a sense of causation, the temporal density is really important. How can we measure this at the temporal density that's appropriate for the time scale for the construct we care about, right? If you're talking about diet, you need to be measuring it pretty often, right? Versus if you're going to be measuring the built environment, it probably doesn't change that much, right? But how do you take that into account with your thinking, right? So here's some classes of sensors, and then also I think some places where I think some really good work is going on with this. So obviously there's wearables. I think everybody here knows about this, right? And then there's also extensions of this, such as like medical devices like the Philips biosensor patch, which basically replaces all the stuff in a hospital room with that little patch. right? But I think the stuff that's really interesting, if you go into the academic literature, one place to look, although there's many, but one place to look is this Center for Excellence by Santosh Kumar, the Mobile Data to Knowledge Center, which I'm pretty sure Kevin's a member of, right? Yeah. So they are doing some fantastic work on trying to infer concepts that we think would actually influence diet and physical activity. For example, stress, trying to use a wearable, particularly the Microsoft Band, to actually infer when someone is being stressed, to know, is this perhaps going to be a stress-eating moment, and therefore a moment to intervene on that type of intervention, right? And there's many other examples. I strongly urge you to take a look at this website. There's some really cool work coming from that. But another one to play around with is sort of the Internet of Things. You probably have heard this phrase, right? The classic one now is this Amazon Echo, where basically it's these tools that are connected to the Internet that live in your home. And this is now the Nest temperature gauge and a bunch of other things like this, right? But the important thing I want to set up here for health is that there is a lot of noise that we think of as noise, that there's actually signal hidden within this. And so a great group from this is Shwetak Patel at University of Washington. He runs the UbiComp lab. And so he's done a variety of things where he basically has translated noise into signal. And here's a really cool example. So in this room, he could figure out the breathing rate of everyone in this room. How do you think he could do that? What is it that's in this room that could feasibly provide that signal? The Wi-Fi signal. There's basically these patterns of the linkage between this computer or our phone and that, and it creates small perturbations when you breathe that he has actually figured out how to pick up and measure. So an example of translating noise into signal from these Internet of Things, there's a variety of things that are leaving digital traces with us that I think we could actually start inferring some interesting concepts from. So I want to challenge that, particularly when it comes to diet. I think there's actually a variety of plausible places to find more signals than we think, like just getting to doubly labeled water. There's some people who are actually working on toilets where basically it has all the sensors built into a toilet. What a great place to get some really detailed measurements, right? As we talked about doubly labeled water and not wanting to deal with pee, right? So there we go. Another one is Deborah Esther, and she was actually one of the authors on the paper. Kevin and I were on it. So Deborah's been really advocating this idea of small data, but the important thing here is the idea of a digital trace. And so what do I mean by this? Think about all of the digital refuse you leave behind. Your emails, social media, your interactions on the websites, right? All of this is being tracked. And most of the time, it's just companies that take advantage of it for themselves so that they can sell you something better. There is a reason why when you look up something on a website and then you go to another website and they advertise the thing you were just looking up, there's a reason why that happened. It's because somebody's tracking you, right? Deborah is making a strong argument, say, why don't we get our own data back so that we can use it for ourselves? And so Deborah's doing things around, can we give you data back about your mood from email or from food tracking, and basically pull your loyalty card from grocery stores and use that to help understand your food take, right? So this is another source of data that I think we need to be mindful of. And then finally, all of this is moving towards some really interesting interventions, right? Back to this point that I think it's hard to really disconnect these. So this is just one example. This is out at Cornell Tech, Tanzim Chowdhury's lab. This system's called My Behavior. Basically, here's how it works. Imagine the system is watching what you're doing, and it's looking to make small suggestions. So, for example, it knows that you like to you walk from one building in one part of the city to another part. What it will do is it say, oh, I notice you're probably about to go for a walk. It'll send you a notification, say, if you take this slightly different path, it'll take you 3 more minutes, but you'll get a little more exercise in. You want to do it? Yep. Right? And that's the kind of thing that it's looking for. And she ran it with a multiple baseline design. She found some initial efficacy of the concept. So, but these are the sort of things where we're really trying to get into those moments where people have where you can really use the information to help people make these decisions in the moment. Back to this idea of the usable evidence with it. Right? And so finally, the last part that I want to get into with this is actually more of these research platforms that are coming out. So one of them I'm particularly intrigued with is this idea of open humans. It's this idea of actually sharing data across studies. So for one of the first 2 studies we're on, this was the American Gut Project and the Personal Genome Project. So here's the cool thing. You sign up for the American Genome Project, the American Gut Project, you get your microbiome checked, and then if you sign up for the Personal Genome Project, all of your data from the American Gut Project is transferred over, if by permission, of course, to the Personal Genome Project, right? And then if you sign up for another study, now all that other data gets shared. And you can start sharing data across these studies. So thinking about that multi-level impact, this type of tool becomes very, very important for us. We start to be able to learn about people across these different studies. We stop thinking about them as isolated, going back to the weather analogy, right? This is allowing that to actually start connecting across these things, right? So this is an important technology actually from a research standpoint that I think we should be very mindful of, things like this. But now this is now setting up the need for theories, right? So from descriptive conceptual models to predictive and explanatory models, right? And I think David actually, I think, set this up really well, right? Our models have classically said things like model structure, predictions, right? A general framework, right? But computational models, they're exciting because they allow us to feasibly articulate hypotheses about dynamics. And I'll get to this in a moment, what I mean by that. And also this multi-dimensional state spaces of generalization. And really, why this is important, it allows you to falsify complex predictions, right? If there's a complex problem, you need something that actually allows you to create the model that makes those guesses so that you can actually test those predictions, a la weather, right? But then it also enables you to do simulation, right? So say you don't have data yet, at least you can do some gut checks like, whoa, that didn't work the way I expected. And now you realize that your world isn't working the way you think it is. So this is just one example. This is social cognitive theory for those of you more in behavior change. We basically created a mathematical model of social cognitive theory. And in terms of the competing demand, so this isn't published yet, but what we're working on right now is basically this model didn't work the first time we tried it. We were trying to represent what we thought Bandura said, but we're finding it didn't work. So now we're actually simplifying it. And we're basically going through a series of competing hypotheses, or competing models that better explain the data. And I'll get to a second on what the data describe. But what it allows us to do is it allows us to make these complex predictions and then falsify them against data and see which one actually is better describing them, right? So now, why is this interesting? Why is this important, right? It allows us to get into some really interesting, novel, new places, right? And I think I've seen this already in poster sessions, other places, so I think this is going to be talked about. But the idea of these just-in-time states, right? You know, there are moments when you are vulnerable to excessive eating, or there's also opportunities when you might be able to do healthier options, right? But what are those moments, you know? That actually is an important target for theorizing in and of itself, you know? And so this is what that multidimensional state space is about, which we have a paper that came out about it. But it's basically about asking the moderation question on crack, right? It's like not just, you know, is it gender, but it's really when, where, with whom, in what state of the person does this particular intervention produce the desired outcome? You know, or another way to think about it is the teachable moment, but on crack, right? It's like teachable moment, if you actually dig into that literature, it's highly underspecified. It's not really, it's kind of like this almost truism. But there's ways to actually mathematically specify this. And so this is a visual of an example, right? Like let's just imagine that you're trying to send a text message to tell someone to go for a walk, right? So there could be three factors: how stressed they are, their opportunity to go for a walk in the moment, and then if people are around or not. Each one of these has an impact on the probability that when that notification is sent, someone would actually go for a walk, right? And so theorizing not just about the dynamics of the behavior, but also the dynamics on when an intervention would work or not is also a really important part of the theorizing. And then as a logical extension of this, getting into this linkage to the physiology and the thermodynamic, the physiology and understanding energy balance is just a part of that equation. But we need to actually be building these models in a way so that they can actually be connected as such. So that's another point of this. So finally, getting into our research methods, right? Going from a causal descriptive to a causal explanatory model. This is not a new concept. This is right out of Shadish, Cook, and Campbell. But the example they gave about this is like the difference between having a causal inference by you can flick a light switch a whole bunch of times. Imagine that's basically your experiment, right? Every time you flick it up, the light turns on. Every time you flick it down, it turns down, right? This is good. You have a causal descriptive model. You have a sense that if I flick this switch, the light turns on. But you don't know how or why that happened, right? You need to have a mechanism of this. You need to understand the flow of the information on how that actually works. And so for this to me is actually, particularly now that we have all these digital technologies, we're increasingly getting to a place where we can start actually much more actively embracing causal explanatory models and studying them in context. And so let me show you what I mean by this. Like this is, in essence, you can imagine that this is sort of the kind of logical black box that usually comes out of RCTs, right? We have some type of intervention. Let's say we're just doing walking reminders for now. And then we measure physical activity, often like once a week, every 6 months or something like that. And then after 12 months, we're like, oh, did their VO2 improve, or BMI or whatever measure you might care about, right? There's a black box. There's a black box here on how this actually could work, right? But let's just say it's a walking reminder. just thinking causally, what is the very next thing that should happen if someone sends a notification? Someone should go for a walk. If they didn't walk after they got the notification, it's probably not working. Now you can make the argument, yeah, well maybe they'll think about it and then they'll do it a little more the next day. Fine, you can model that. But just be clear about what those proximal outcomes might be. It allows you to build these causal pathways to actually carefully understand this. So how do you do this? That's the important question, right? So this now getting back to randomization, right? This is, I'm not going to take no credit for this whatsoever. This is Susan Murphy. She's literally a MacArthur genius. Have a paper that we've been arguing this idea of a micro-randomized trial. So basically what it is, it's a factorial design. So just like randomizing people, but instead what you're doing is you're randomizing at the decision points. So like say, for example, you want to help someone set goals. So each morning you can randomize if you're going to help someone, give someone a goal or not, or help them plan or not. Or one of the ones that we did is we gave context notifications. So 5 times throughout the day, we sent these little triggers to help someone walk more in a given moment, right? Those things you can actually randomize on if they're going to work or not. Now, what it does is it allows you to get each one of these components, and just like with a factorial design, you can actually randomize multiple things simultaneously. So you can actually have, the one we're just about to run has like 4 different things that are randomizing within day, 2 things at a daily level, 1 thing at a weekly, and then 1 thing at a monthly level. So I think we have like 8 conditions that are going on, right? Talking about mapping the complexity, we're getting a sense of how that actually all interacts with each other, right? And ultimately, again, multiple things to randomize, and you can randomize hundreds to 1,000 times within a short time period. So what we learned from this is the interesting stuff, right? We get a main effect. Does a notification work? But more interestingly, we get a sense of does it work over time, right? And this, you probably know this, right? Our data right now are showing like those notifications, they work really well in the beginning and then they diminish by the end. We can tell you mathematically exactly how much from this trial with good causal inference. We can also tell you about moderation, of course, but I think the more interesting one is the time-varying moderation. We can actually test that multidimensional generalization space idea because we can actually articulate that, right? When people are really stressed, does that notification not work anymore? We can test that in our data experimentally. It's pretty exciting. So another example of this, and this is actually where the computational models come into play. This is from control systems engineering. It's called system identification. The long and the short of it is, we all know that, I'll go back to this other slide for a second. We all have this recognition that when you're helping someone set a goal, right, you don't want it to be too hard, because that'll be demotivating, but you don't want it to be too easy. You have to find this sort of ambitious but doable range. Well, that's actually a pretty wicked, complicated idea. Like, how do you know what's an ambitious but doable range, right? So what you do is you can randomize. Sometimes you give people high goals, sometimes you give them low goals, sometimes in between, right? And what this allows you to do is it allows you to actually start to build an understanding of not just if there is an effective goal setting, which I think there's plenty of data to suggest that there is, but instead, how does it work in practice? How does it interact with individual differences and so forth? And so this is yet another experimental design, and it allows us to study things like testing these really dynamic hypotheses. And I'd be happy to talk through what this actually means, but we have a pretty well specified dynamic hypothesis from this that's articulated in our mathematical model now. And it also allows us to study the multi-generalization space. So coming back to our takeaways, we are moving from a data poor to a data-rich science. And so in my opinion, what that sets up is because we are focused on health and humans, we need to be thinking not just about taking advantage of the technology so that we can learn great science, which is good and important, and we need to complement that with what is it that the people need from our science, and making sure that we're creating that, we're being mindful of that in our decision making. And then doing it requires a shift in our measurement theories and methods for causal inference. So those are my takeaways, but I want to now pose 2 questions just to throw out some more fun things. So what about, because I didn't get a chance to dig into this, but I just want to set this up. What about patient-led engineering and science? So this is Dana Lewis. She developed her own artificial pancreas. She actually talked about this stage right here. She was standing right here a few months ago. She built her own artificial pancreas from off-the-shelf technologies. It's pretty badass. What does that mean for us, when patients are doing stuff like that? Okay, and then another question, how are we going to curate this, right? Particularly precision medicine sets up a major problem to disparities, right? If you can't get the right information to the right person at the right time, you're going to be screwed and you're going to be creating problems, right? So how do we do this? And so Susan Mickey just got funded on developing an ontology for this. So this is back to that jingle jangle fallacy, this idea of we're not talking about the same thing. First thing you need to do is just agree on terms. When you talk about diet, what do you mean? And what are the many, many logical sub-branches of the tree going on with this? So in information technologies, that's called an ontology, and there's a way to do this, and I won't go into the details, but it's important for us to be mindful of how we actually curate the information. There's tech companies that are doing this as well, and then also the stuff that I've been working on is called Agile Science as a methodology, but it's basically about trying to, that you've seen some bits of this already, but it's basically about setting up this need of making sure we are carefully designing this evidence base, not just so that it solves the one problem for the person in front of us, but also that it can curate and generalize, and particularly for those people who are most in need. So, but I think this is actually one of the hardest problems that we need to be careful about, particularly when we get into things like precision medicine and the role of technology. So, thanks. Let's discuss.